if you're nervous about Google, you don't have to worry about asking questions in the chat. That's not, some people get nervous, but like I don't publish those. So feel free to ask your questions is what I'm getting at. Want to welcome everyone to today's meetup. I'm so excited about today, mostly because we have attendance of more than 3. But also we have a great speaker and an awesome topic that I don't think I've ever heard addressed, which is kind of funny. We want to thank, as always, Weave for sponsoring us and providing the Google Meet and all of the other stuff that Weave does to sponsor us. No, go back. If you are hiring or looking for jobs, please, as per usual, put them in the Forge Utah Slack on our jobs board. There's like, I think, 10 or 15 open job recs in there right now. So like tons of people are looking. I think that like 70% of them are Go. I know one of them is Java, so you can ignore that one, but most of them are for Go. If you would like to speak, I'm collecting on PaperCall. Please go ahead and put them in there. The only thing I ask is that it not be a joke talk. We pretty much accept everybody that comes through, especially first-time speakers and people who are looking to gain experience. And then lastly, we want to thank Bill for agreeing to speak with us today. I reached out to him and he responded quicker than I really was expecting him to respond. I think it was 5 minutes. So he's super willing to talk to us and help us out today. So I'm going to quit sharing my screen. I don't know why that went white. That's really funny. I guess that's what the last slide does. I'm going to quit sharing my screen. And I'm going to turn the time over to you, Bill. I feel like I don't need to introduce him, but for those of you who don't know, he speaks all the time, pretty prolific. And what I think is most awesome about him is he does a lot of work for the community, especially with the meetups and with conferences with GoBridge and stuff. So like he's really making sure everybody has knowledge and opportunities in the Go community. So time's all yours, Bill.
Brilliant. Thank you for having me. Thank you for that introduction. Yep, my name's Bill Kennedy. I have a small little company in Miami called Ardan Labs, A-R-D-A-N Labs. And if I'm not in training and you send me an email, I probably will get back to you within 5 minutes. It's important to me to get back to people and set that expectation. That being said, what we're going to talk about tonight is, I think, an important topic that really will help you kind of understand the things you need to be thinking about semantically around behavior with the schedulers. Now, there's an operating system schedule involved, and then there's a Go scheduler involved. We're not going to go too deep there. But what I want to do is kind of go through the scheduler semantics, the behavior of the schedulers, and tie in a lot of that multi-threaded programming concepts that we need so we can predict how our programs are going to run. And this is going to help you better kind of architect and design your multi-threaded software. And I've got some programs that we can benchmark when we're done to validate the things that I'm going to share with you. Okay? So what I'm going to do is, I'm usually in front of a whiteboard. It's kind of where I like to be here. I'm going to go over the screen too. But I don't have a whiteboard. What I have is my Lucidchart app. So hopefully everybody can see that right now. And I'm going to work on that. I'm kind of blind to what you're seeing, so I do need help. If you can't see something that's not large enough, I need you to speak up. Now, here's the next thing. I can see the chat window on this meetup. So if you have a question, go ahead and write that question into the chat. I'll be able to see it. I'll try to identify that I recognize the question, and then I'll try to get you an answer as soon as possible within the flow of the talk. One nice thing to be able to do also is to chat amongst yourselves, but if we use this chat window for that, I may miss your question. If everybody's on Slack, it's always a really nice place also for everyone to kind of talk about what's going on. All right, that being said, and the hour that I have, and I never have enough time, let's get going. So I think there's a few things that are critically important for you to have a solid semantic understanding of as it relates to the scheduler and multi-threaded programming. We're not going to get into the mechanics of how a scheduler works or an implementation detail. That's not going to make you a better Go developer, but being able to understand behavior will. And I'd like to kind of start this conversation off with maybe a theoretical conversation, or maybe something you had to do in university. Let's imagine that we have been asked to write a scheduler that can create the illusion, even if it's not physically possible, to execute multiple pieces of work at the same time. So let's kind of define some things here as we go along. I'm going to use the whiteboard here. So we can do this. And what I want to do is, right now, let's say that the hardware that we have to work with, all right, is a single threaded piece of hardware. So what does that mean? It means that since it's single threaded, we're only really able to execute physically one piece of work at a time. If I want to be able to execute more than one piece of work at a time, I would need another processor. I would need a processor with another hardware thread. And so what we're going to do is define right now that our hardware is single threaded. Why don't we define what the word thread means as well, and what I also mean by work. A thread in this conversation is going to mean a path of execution. A thread's job is to be given a series of instructions that need to be executed on this hardware and make sure that it happens. And so when I say that we're talking about some piece of work, what we can also then say is that for every piece of work that we want to get done, we need a thread assigned to that work, and then that thread has to be assigned to the hardware in order for the work to physically get executed. One of the important things here is that the only platform that really exists is the hardware, because it's the hardware that executes instructions. At the end of the day, we can build as many software layers as we want on top of it, but the hardware is the real platform. And our platform is single threaded. All right, so the fact that we can only execute one piece of work at a time shouldn't get into the way of the fact that I want to be able to create the illusion with my scheduler that multiple pieces of work are actually executing, even if I physically can't. Now, what is one strategy that we could leverage to make or to create this illusion? So one of the strategies that we could leverage is this idea of defining what I'm going to call a scheduler period. Let's say for now our scheduler period is 1,000 milliseconds or 1 second long. Now, what does that mean? What it means is that what we're going to do is, given the amount of work we have for any given scheduler period every second, we're going to try to make sure that all of that work gets some time on the hardware. This is how we're going to create the illusion. Now, let's see if this idea works by kind of running a simulation here on the board. Let's start actually, let's back up one more second too as we start. We said that a thread is required to get any sort of work done. So let me just take this box here and put it over here, because that's going to represent our thread that's doing work. But before we start, I've got to define at least one more thing. We've got to define the different states that a thread can be in. And there are 3 states here that are really important. we're going to say that a thread can be in a running state, all right? So when a thread is in a running state, what we're saying is that we've put it on the hardware so it can go ahead and start executing its assigned instructions, or AKA its work. A thread can be in a runnable state. When it's a runnable state, it's not on the hardware, but it really wants to be on the hardware. It's the runnable threads that we care about from our schedule. Because for the beginning of every schedule period, we want to look at all the threads that are in a runnable state and make sure that they all get a chance to run. The final state is a waiting state. And from our scheduler perspective, I couldn't care less about threads that are in a waiting state because they don't want access to the hardware. They're not a concern. Why would a thread be in a waiting state? Maybe it's waiting for the operating system to finish some sort of disk read. Maybe it's waiting on the network for something. So there's lots of reasons why that thread might be in a waiting state. What I care about right now are threads in a running state. So why don't we do the following? Let's say that we've built our scheduler. Let's build our scheduler. And as the scheduler turns on, as the operating system boots, let's say that what we have right now is just one thread in a runnable state that needs to be executed on the hardware. Well, that's not that big of a deal, right? Because what we can now do is say, no problem, thread. You're going to get the full time slice or the full 1,000 milliseconds we have right now to do your work. This is going to be billions of instructions, actually, that this particular thread is going to have an opportunity to execute. It's a large amount of application or thread throughput. I'd like to think about that thread throughput. This thread's going to be able to execute billions of instructions in that time. All right, brilliant. That's done. The thread has executed its time. We're back now to the next scheduler period. So what's next? Well, let's say that for the next scheduler period, 2 threads are in a runnable state. What is that going to mean? Well, what that's going to mean is that if we want to create this illusion on our single-threaded hardware, then we're going to let this one thread here, and maybe what I can do to give us a little bit better visual, we'll paint this as the purple thread, right? So the purple thread is now going to get, in this particular thing, this thread got the full 1,000 milliseconds, right? But now the purple thread is only going to get 500 milliseconds. It's only going to be able to execute half of the same amount of work it did before, because essentially what we have to do here is give the pink thread the other 500 milliseconds. Now, this is still working, right? I mean, it's creating this great illusion that this work got done because we put it on the hardware, and then this work got done. They're still executing billions of instructions. Can nobody see this? Nobody see the work I'm doing on the whiteboard here?
Okay, it's clear. I can see it.
All right, good. So far, this is working incredibly well, because to the human eye, it's going to look like both pieces of work, both threads, are doing a tremendous amount of work in that 1 second. All right, let's keep this going. So what do we want to do next? Let's imagine now that we've got 10 threads in a runnable state. What does that mean? All right, well, that means now that the purple thread has to come down to what? Got to kind of come down to about 100 milliseconds. And then the pink thread, well, we're going to time slice that down to 100 milliseconds, right? There we are. And then we know that we've got another 8 threads, okay, that need to also time slice. Maybe we'll just show the rest of these as yellow. But the remaining 800 milliseconds needs to be divided up again 8 times, right? Now, at 100 milliseconds, I mean, we're still talking about maybe 1 million instructions. Like, the throughput for each piece of work is still really good. I'm really still happy with this idea that we have of time slicing this work across the scheduler period And at 10 threads, we're still getting excellent work throughput. All right, let's speed this up a little bit. What if we have 100 threads? What does that mean? Well, it means now that our purple thread is going to drop down to 10 milliseconds. And our pink thread is going to drop down to 10 milliseconds. All right? We can even try to even show this visually a little bit more down there. But what about the other 98 threads? Well, once again, we're now going to have essentially, right? We had essentially 8 threads here. We're going to have essentially 98 threads here needing to consume the other, consuming the other 980 milliseconds, right? It's 98 basic context switches occurring on the hardware to get all that work done. All right, that sounds maybe reasonable. I don't know. Let's think about it. At 100 threads, do we feel like 10 milliseconds is still giving us enough thread throughput to feel like there's a lot of work getting done? I think so. And the reason I think so is because we're still talking about hundreds of thousands of instructions being executed within this time. And so far, even at 10 threads, at 100 threads, life is good. But watch what happens now. What if we get to 1,000 threads? What does that mean? I think things start to break down here. Because now what we're talking about is this thread essentially getting just 1 millisecond. This thread is getting 1 millisecond. And now we've got 998 other threads getting the remaining 998 milliseconds. So for me, we're starting to have some problems with this illusion. One, primarily, each thread at 1 millisecond really isn't getting enough time to get a strong enough amount of work done to create this illusion. Two, even after this thread runs for 1 millisecond, even if it was able to execute hundreds of thousands of instructions, it's waiting essentially a full second before it even gets to run again. We're really starting to have a problem here in creating this illusion. And don't even get me started if I get to 10,000 threads, because I'm not going to draw this all out. But we're now talking roughly like 100 microseconds per thread and waiting a full second for the other 9,998 to run. So what happens is, right, what happens is that at some point in time, and from my perspective, at least in what we're doing here, that we have some sort of breakdown in a point of diminishing return on the number of threads that we can really have in a runnable state for schedule period. Because once we get below a 10 millisecond time slice, we're just not giving each thread enough time to execute instructions. And there's having to wait much more time than is reasonable. So how could we potentially solve this problem? There is something we could do. We could add another knob to our scheduler, and we can call it the minimum time slice. And maybe what we do is we set that to 10 milliseconds. Maybe what we say is, look, we want to define a schedule period of 1,000 milliseconds, but you know there's a point of diminishing return under 10 milliseconds. So once you get over 100 threads, even at 1,000, it doesn't matter we're not going to let that number go below 10. We're not going to let this number go below 10, which means that these other 998 threads also can't go below 10, which tells us what? It kind of tells us that our scheduler period now in this particular situation isn't 1 second. It's now also growing at an order of magnitude, right? Now it's going to take 10 seconds to get all these threads executed if our minimal time slice is 10 milliseconds and there's 1,000. This is going to take 100 seconds. But wait a second, let's step back. What was my job in designing the schedule? It was to create the illusion that we can get all this work done, right? And even if we can only execute one path of execution, one thread at a time, this was my job, and I'm doing it. Is it my fault that you, the user, is throwing 1,000 or 10,000 threads at me? No. So one of the first things that I want to kind of talk about at this point is the idea that less is always going to be more in these multi-threaded environments. The less threads we have to worry about trying to execute within the scope of the scheduler period, the more time each thread's going to get, the more each thread can have that application throughput, the healthier the system's going to feel and look. You start giving me 1,000, 10,000 or more threads, there's not much I can do right now when I've got this scenario. So we really want to try to minimize the number of threads that we have. Now, let's step back because there's a lot more to talk about. There's some other costs here. Stuart, can you mute for a second for me, please? Thanks. There's some other costs here that I'm not talking about, and that's the cost of a context switch. Look, there's a scenario where we've got a thread running on the hardware. Every one of these little lines, and there's 98 of them here, and there's 998 of them here, and there's 9,998 of them here, which I didn't draw. But each one of these lines, these demarks, right, they represent a context switch. That's taking the thread that's on the hardware off and then putting a new thread on. That's not free. Do you know how long it takes to perform a context switch in Linux, or at least what's been measured on average? What's been measured for a context switch is roughly, get this back here, 1 to 2 microseconds. That's what a context switch kind of costs. Now, I'm going to use 1 microsecond to be conservative, which means that this microsecond ends up really costing about 12,000 instructions. It is so hard to think about latency and time. I like thinking about latency as instructions lost. So how can we do that? Let's go real quick to Go training. And let me bring up something that will really allow you to kind of get an understanding of the cost of things. Here. I'm just going to focus on this. Now, most of us, if we're running a 2, 4, or 6 core processor, probably have our clock speed at 3 gigahertz. I've got an 8-core processor that runs at like 2.5, but that's not important. What's important is we can use these numbers. So if your processor is clocking at 3 gigahertz, what that means is that every nanosecond that goes by, 3 clock cycles occur. And you need a clock cycle for any work to get done on the machine. Now, thanks to the modern hardware and compilers, we should be able, on average, to execute 4 instructions for every clock cycle. And this is the magic number. I always want us to think about a nanosecond of time being worth 12 instructions. 12 instructions you either executed or 12 instructions you didn't. That's our latency. This is how we can convert time into something we can rationalize. So if I said you had a nanosecond of latency, it means that you had 12 instructions of latency. If you had 1 microsecond of latency, that's 1,000 nanoseconds. That's 12,000 instructions lost. You can do a lot of work in 12,000 instructions. 1 millisecond, that's 1,000,000 nanoseconds. That's 12 million instructions lost. And the second is up to billions. And this is why when we're looking at this diagram and I'm saying 10 milliseconds is still reasonable, because we're talking about 120 million instructions that we can execute within the scope of that time. That's pretty good. Just when we start getting under that, we're not necessarily going to see the throughput that we otherwise could. So when I tell you that a context switch, taking this thread off and putting this thread on, is costing us 1 microsecond conservatively, we're losing 12,000 instructions to do that. That's 12,000 instructions that we could potentially be using for something else. So it's not even just the cost of time that each thread wants to take. We also got to add into it the cost of time to pull the thread off and to put the next thread on. It's not cheap. Okay. Now, understanding this, there's more I now want to add to it. There's really 2 things you are responsible for as a multi-threaded software developer that your language or your runtime or nobody else can do for you. One is you have to manage the synchronization and orchestration of these threads. Now, we're not going to get into that in this lecture, but synchronization is about synchronizing access to shared state, getting in line, taking a turn. And orchestration is about threads having to communicate with each other. That's like getting up to a cash register after waiting in line, synchronization, and then talking to the person behind the register and exchanging money and product and all that. That's orchestration. You're responsible for that. That's another class. There's something else here that I do want to talk about that you're also responsible for. And that is understanding the type of work that you are doing. I cannot say this enough how critical that is. You must understand the kind of work you are doing, because if you don't, all of this can collapse on you, or all of this could work for you. In other words, there's latency here. What we need is either the latency working for us, or we need to get the latency out of the way. Your software isn't as fast as it otherwise could be because of latency. So either latency is working for us, or it just can't exist at all. What's beautiful about Go, working on networking type of software, there's just inherent latency waiting on networks. And so we can do a lot of things around the latency working for us. But if you were going to write an operating system driver, if you were going to write maybe a browser, we've got to get latency out of the way. This is why languages like Rust can really be excellent for writing an operating system driver, a browser, because Rust is a language that allows you to basically get the latency out of the way. Go is a language that's really about making latency work for you to your advantage. So it's there, but it's not really hurting you. That's another conversation, but we're going to leverage that idea here as well. So the other thing that you're responsible for is the type of work you're doing. And there's 2 types of work that you could be doing at any given time. The first type of work we're going to call CPU-bound work. CPU-bound. The next type of work, and there's only 2 that we have to keep track of, is IO-bound type work. Each of these types of work have different semantics and require us to architect what we're doing differently. And I want to say one more thing. The only reason we even write multi-threaded software, because it's so complex, the only reason to write it is because your single-threaded software just isn't fast enough. And so this is a game of complexity versus performance. And at some point, the added complexity isn't going to be worth the added performance. And if you don't get better performance, definitely you don't want the complexity. Let's just be very clear. We're only adding this complexity because one thread isn't fast enough. If it was fast enough, you would never do this to yourself. So we've got CPU-bound workloads, and we've got IO-bound workloads. And we need to understand this in order to better understand how to architect our software, because we're looking for performance. Now, let's describe what a CPU-bound workload can be. A CPU-bound workload is any workload where the thread doing the work never naturally moves into a waiting state. The thread is not doing anything, not executing any instructions that would cause it to move into a waiting state. What's an example of a CPU-bound workload? If I asked you to write a function that calculated Fibonacci numbers, that's a CPU-bound workload. You're just doing math. You're just doing math. There's nothing that that thread is going to be requesting to do the math that will cause it to move into a waiting state. That is CPU-bound. What's an IO-bound workload? IO-bound workloads are workloads where, let's say I gave you a collection of files to open and read, to process. That's IO-bound, because the moment you go to open that file, the moment you go to read that file, we're making a system call, which is going to cause the thread to go into an immediate wait. It doesn't need the CPU when it's waiting. So it goes into a waiting state. That's IO-bound. Now, why is that significant here? Well, I need you to understand something. This diagram that we started with, that we drew out, kind of represents something that is most likely not reality. This diagram is assuming, all the way down to even 10,000 threads, that every thread is doing CPU-bound work. The only way we would get to this 10-second or 100-second scheduler period is if all 1,000 or 10,000 threads were doing CPU-bound work. And that's just not the reality of life. It is really rare for most of us to be doing CPU-bound workloads. We much more, especially if you're writing code in Go, you're really much more focused on IO-bound workloads, which means that even though this thread has a 10 millisecond time slice, it probably won't use it. There's a good chance that it only uses, I don't know, 100 microseconds, because it's going out and trying to fetch some data off the internet, which means that 100 microseconds in, it finally made that get call, which takes it off the hardware, which means that maybe this thread, maybe if we're really lucky, only runs for 1 millisecond, because it too is maybe trying to read something on disk, and that's where we're at. The reality is that I could potentially have 1,000 or 10,000 threads running efficiently if they're all doing IO-bound work and not using their full time slice. Again, that's the majority of the work that we do, which means that this bar does still exist, but it's probably down here when we get into 50,000 or 100,000, because eventually, no matter what, there is too many threads trying to share this hardware within this scheduler period with the cost of those 12,000 instructions. So this is one of the reasons why it's so important. And again, we do mostly IO-bound workloads. Now, I want to explore this idea of CPU-bound and IO-bound workloads. But before we do, with everything that we've learned so far, I want to define two more terms that are critically important to our understanding here. And I think these are terms that are misunderstood by too many people. So I'm going to be giving you my definition for these, and at least these are the definitions we're going to use for this talk. The first word is parallelism. What parallelism means is that two or more threads can execute their instructions physically at the same time. Now remember, in our model here, we are single threaded. We have a single threaded piece of hardware. So I can't do anything in parallel here. If I want to do something in parallel, I need a processor with more cores and more hardware threads. Now I can physically do something in parallel. One thread can be executing instructions here, while the other thread is executing instructions here. If I want to do more in parallel, I need more. I want to do more in parallel, I need more. I want to do more in parallel, I just need more. Okay, so parallelism means that we're physically able to execute multiple paths of execution, or different threads can execute in parallel at the same time, and this requires hardware. So the other word is concurrency. What does concurrency mean? Concurrency means one thing, and I want to type it out here because it's that important. Concurrency means undefined, out of order execution. This is what concurrency means. It's going to mean to us. I want you to sink that in. Undefined, out of order execution. In other words, given a series of instructions that we need to execute, we should be able to execute those in any undefined ordered way and still get the same result. If we could take a series of instructions or a series of steps and execute them out of order in this undefined way and get the right answer, then we have something we can do concurrently. Here's the thing. Concurrency sometimes needs parallelism to realize better performance. And sometimes concurrency doesn't need parallelism to realize better performance. Sometimes concurrency and parallelism have to come together. Sometimes they don't need each other at all. And this is what I want us to learn. This is what I want us to understand, because that idea is also built around the idea of whether we're doing CPU or IO-bound workloads. Okay, so let's do the following. Let's go ahead and let's start with a CPU-bound workload. So what is a CPU-bound workload that we could maybe define and play with here on the board? Let's say this. Let's say that we have 1 million integers. I have 1 million integers, and I want to add them all up. My hardware can't do anything in parallel. It's a single threaded piece of hardware. Now, let's talk about that. Let's say I wanted to write this algorithm first as a single threaded algorithm, which I do recommend that you always do. All right. How many lines of code would it take to write this function if we're just using one thread? Think about it. Probably only takes about 5 lines of code. Variable declaration, var sum in, for range loop to range over the ints. Inside the loop, every integer we range over, add it to sum, and then return sum. It's 5 lines of code, right? I mean, I can make this argument that we're dealing with 5 lines of code if we're working with this one thread. We could keep that code in our head. Easy, right? We can maintain this. And when we think about the execution of that work on our single thread, let's take our purple thread here, just to have some fun with color again. We know that there are no context switchers. There's nothing we need to do because we only have one thread and it does the entire amount of work. So this is cool. There we are. Now, question. Always ask this question. We have a single threaded version of the algorithm, which is roughly about 5 lines of code. Can this work be done concurrently? What am I asking? Can it be done out of order in this undefined, not random, just in a different order every time that is not defined? Can we? Does it matter what order we add the integers up as long as we add them all up? The answer is no, Bill. It doesn't matter what order we add them up in as long as we add them all up. Then this is a piece of work that can be done concurrently. Okay, how could we do it concurrently? Well, we could take this strategy. Could maybe use 4 threads where we have each of the 4 threads maybe get their own slice or bucket of those million integers. And they each kind of work on their own set, right? So we could do that, right? You're going to get the first n number of integers from that collection. You're going to get the next. You're going to get the next. You're going to get the next. And we'll just kind of try to divide that up evenly. Okay, brilliant. How many lines of code do you think it's going to take to write that algorithm? Well, I can't even keep all that in my head. But I'm going to just take a guess that we're probably looking at about 40 lines of code to write the concurrent algorithm with 4 threads, as opposed to 5 lines of code with 1. But an order of magnitude more complexity in terms of code. But remember what we're doing. Why are we even here at all? Why are we trying to write multi-threaded software? Because the single-threaded algorithm isn't fast enough. We need it faster, so we'll take the complexity cost. But here's the rub. This is a CPU-bound workload. Based on the fact that we cannot leverage parallelism, we use single-threaded hardware. Which algorithm's going to run faster? The single-threaded or the 4-threaded on this hardware? Guess what? You know which one runs faster? This. This is the one that's going to run faster. Why? I thought concurrency is supposed to make things faster. Remember, this is a CPU-bound workload. Remember, this thread is executing the addition of integers non-stop from beginning to end. What are these threads doing? They're constantly stopping and starting. If we're lucky, which we probably won't be, there's only 3 context switches here. But there's a good chance that there's going to be more. Remember what a context switch costs you. Context switch costs you 12,000 instructions. So every time the scheduler chooses to stop one thread, to start another, to start another, to start another, to start another, every single context switch is costing you 12,000 instructions that we could have been using to add integers, but we're not. We're using it to take threads on and off the hardware. So here's a case where concurrency isn't really giving us better performance. But why? Because when it's a CPU-bound problem, concurrency can only give you better performance based on the amount of parallelism you can throw at it. In other words, if I change my hardware to be like this, now what's going to be faster? Well, this now is going to be faster. Why? It's going to be faster because 2 threads can be executing their adds at the same time. So that means that we're getting twice the amount of work done in the same amount of time. Brilliant. But I'm not just looking for fast. I'm looking for the fastest. How many threads in our CPU-bound workload that we're able to do concurrently, how many threads are going to give us the absolute best performance? In this scenario right now, because I can only run 2 threads in parallel, the answer is 2. If I want to be the fastest with 4 threads, what do I need? I need to be able to run each thread independently. That way, all of the latency related to the context switch is gone. So here's something nice about CPU-bound workloads. They are really efficient to execute. And they are kind of easier, though that's a bad word to use in any of this because it's complex. But they're easier to reason about. Because if we say that this can be done concurrently, and then we say it's CPU-bound, then we can say, well, how much concurrency can we throw at it? And the question is, well, how many threads can I run in parallel? I can run 4 threads in parallel. Then you can throw 4 threads at it. Oh, no, I can only run 2 threads in parallel. Guess what? Now you can only run 2 threads at it. Because if you use less than 2, we've got hardware that's not being used, idle time, that's not helping us. If we use more than 2, then we've got context switches that are slowing us down. And so CPU-bound workloads are beautiful workloads. They're the most efficient workloads we can do on the operating system. They produce the least amount of load. Love them. What's the problem? I already told you. We don't get to work on CPU-bound workloads. We work on IO-bound workloads. I wish life was like this all the time. It's not, but here we are there. Okay, let's change a couple things up. Let's go back to our single-threaded hardware, and let's focus on an IO-bound problem. So instead of 1 million integers, let's say that we're dealing with 1 million URLs. Now, let's go back to where we were before as well. Let's say that we're going to use, the first question again is, if we need to process 1 million URLs, can this be done concurrently? Does it matter what order we process the URLs in? If the answer is no, then we can use a concurrent algorithm. Now, to do this with 1 thread, probably looking at 10 lines of code to do it, if I had to just guess off the top of my head. The concurrent algorithm is probably close to 40 lines of code again. Maybe it's 50 lines of code. You see that difference, a lot more complex. But let's get back. IO-bound workload, 1 million URLs, single-threaded hardware, no parallelism at play. Which algorithm is going to run faster? In this case, our concurrent algorithm with 4 threads will run faster. Unlike we saw with our CPU-bound workloads, concurrency, when it comes to IO-bound workloads, does not need parallelism to see better performance. CPU-bound workloads need parallelism, and the amount of concurrency will match that. IO-bound workloads don't need parallelism to see better performance. Why? Because this 12,000 instruction latency cost on the context switch is now working for us, not against us. You see, when this thread here falls into its first context switch, I mean, literally when it falls into its first wait state, it might be about, let's say we're lucky, it's 100 milliseconds in, and then it makes the URL call and it has to wait. For that amount of time that it's waiting, it's not doing any work. No work is getting done until eventually it comes back. And then we can process that, make the next call. And so these gaps in time are not letting us be very efficient with time. And this is going to cause us to context switch too off the hardware because the hardware wants to run stuff. So the fact that this thread is constantly going in and out of running and waiting, we're slowing down. What gets to happen here is beautiful. What happens now is this thread does its time, just like this thread. But at the moment that it now goes into a waiting state, our scheduler comes in and immediately brings the next thread in. So even though we're going to have a 12,000 instruction hit here, it's better than what we're probably experiencing here, which could be hundreds of thousands, if not more, instructions of latency. And so in this case, that 12,000 instruction hit on the context switch is working for us, not against us, because it's allowing this hardware to stay busier doing application work as opposed to what we are experiencing here, which are potentially larger gaps of not doing work as doing work. Really amazing. But I just don't want to be faster I want to be the fastest I can be. How many threads should we throw at this problem to be able to run the fastest on our hardware? This has been a problem forever. We might never really know, because this is the formula for running at your peak performance in this IO-bound environment. For every hardware thread, one thread should be in a running state. One thread should only be in a runnable state. Do it this way. So for every hardware thread that we have, right, one should always be in a running state. Only one should be in a runnable state, and all other threads then should be in a waiting state. If we ever have no threads running, we're not getting any work done. If we ever have more than 2 threads in a runnable state for each hardware thread, then we've got load. We've got to find some magic number of threads that keeps this formula intact for every hardware thread we have. You know how impossible that is? It's impossible. Why? Because the work we do doesn't tend to be this uniform. We have services with lots of different APIs that get executed differently throughout the day. And each of those APIs have a different latency cost and load cost altogether. So it's really hard to find this number. So what are we supposed to do? Well, if you were coding a web service like this in a programming language like C, you can't just throw a thread at every request that comes into the service, right? You can't do this model. You can't say, let's throw 50,000 threads or 100,000 threads, one per request, because we already know what's going to happen, even if it's IO bound. It's too much load. So what you do at the operating system level is you create a thread pool. And you say to this thread pool that this number of threads, whatever it is, some magic number, whatever it is, you're going to handle all of the work that comes in. And we try to create the pool size to give us this to the best extent possible, which again is really quite complicated. Now, one of the things that Go did was eliminated our need to use thread pooling to run IO-bound workloads efficiently in a concurrent fashion, regardless if we have one hardware thread or more. What Go does, and if we had time, we could explore that. What Go does is allow us to have 50,000 Go routines, 100,000 Go routines. A Go routine is nothing more than an application level thread. It has the same semantics as an operating system thread. And one of the beautiful things about Go is we can use that sort of model of just throwing threads at a problem and not necessarily experience this same stuff that we are experiencing, let's say, at the operating system level. It's really cool. We had time, we can explore that. But without a scheduler like Go, we're kind of bound to the thread pool to maximize our CPU efficiency, and it's never going to be super efficient. And yet Go knows that the majority of the work we do is IO bound, and they've helped kind of solve some of those problems. But the big takeaway that I need right now, so we can look at some code, is the following. We must identify, I'm going to stop sharing for a second. I need you to identify, are we doing a CPU-bound workload or an IO-bound workload? That's one of the first things I need you to understand. If it's CPU-bound, we've got to go in one direction. If it's IO-bound, we go in the next. The next thing we need to do is identify, is the work we're doing, can it even be done concurrently? How can I have something that can't be done concurrently? Think of bubble sort. Bubble sort. Bubble sort cannot be done concurrently. Bubble sort says, go to the beginning of the list and do a linear traversal and flip anything out of order. And then kind of go all the way back to the front of where you started and do it again. And then do it again and do it again until eventually you don't flip anything. That's not something that can be done concurrently, which is why Go uses basically quick sort in the standard library for sorting. Can't use bubble sort for sure. So we're going to identify, is it a CPU-bound workload? Okay, good. It can be done concurrently. Great. Now, how much concurrency can I throw at it? How many threads can I run in parallel? Oh, I can run 16 threads in parallel. Then you can break the work up in 16 parts because we don't want any context switches getting in the way. No, I'm sorry. The workload is IO bound. Oh, well, if it's IO bound workload, can that still be done concurrently? Yes, Bill, it can. Well, if you have an IO bound workload that can be done concurrently, guess what? We don't need parallelism to see better performance. Well, then, Bill, how much concurrency can I throw at it? Well, you're a Go programmer now. So guess what? Who cares? Just throw as much as you want. How cool is that? Just throw as much as you want. Go is there to take care of it for you. Beautiful. Now, I do want to show you this stuff. So I've got some programs here that we can run that you can see. You now should see my screen again, hopefully. I used to be able to see everybody, and I don't know why I can't see everybody anymore. So I apologize for that. But let's get back to this screen here. Now, I'm going to switch this over to some code. This code can be found. You got to let me know if the fonts are big enough. I'll make it a little bit bigger. This code can be found in the Go training, Ardan Labs Go training repo. So github.com, Ardan Labs Go training. Under topics, under Go, under testing, and under benchmarks. And the two we're going to look at is CPU bound and IO bound. But I'm going to do that here in VS Code. Okay. Now, oh, you know, I know what I did. 1 second here. Let me unpin. I was pinning myself there. Okay. So let's start with our CPU bound workload. So what I'm going to do for our CPU bound workloads here is literally what I did on the board. We're going to generate a list of integers that we're going to add. So here's the sequential version of add, all right? Those 5 lines of code that we talked about. Here is the concurrent version of add, which is roughly about the 30 lines of code. I'm not going to walk through the code, but understand you can see already the order of complexity between single and concurrent. And we can specify how much concurrency we want by specifying the total number of Go routines. Then we're going to break the list of numbers up into a different kind of stride. So each Go routine focuses on their own bucket of numbers from the larger one. And to run this, what we're going to do is write some benchmarks. So I'm going to run the benchmarks twice here. But what we're going to do is 5E8. So 8 zeros after the 5. That's how large of a list we're going to use, just so it's a large list to add up. And I'm going to run this in 2 different ways. So this is a CPU-bound workload. Let's take a look at how I'm going to run this benchmark first. So we're going to go into CPU-bound. Now, what I'm going to tell the testing tool is the following. First, we're going to turn off garbage collection. There's no reason to have garbage collection get in the way of these results. Second, I'm going to run this benchmark as a single-threaded Go program. Now, remember, this is what we've been talking about. This is a single-threaded Go program. We're going to run with 1 Go routine, and then we're going to run with 16 Go routines without the ability to do anything in parallel, with a bench time of 3 seconds to add all those up. So what does this mean? What should the results be? CPU-bound workload that we can do concurrently with 1 thread or 16, a thread being a Go routine. But there's no parallelism. Now, I told you that without parallelism here, our sequential or single-threaded algorithm should be faster than our concurrent algorithm. I don't know. Let's see what happens. We're going to be adding a lot of numbers up. All right. So there it is. I mean, we're adding a large number of numbers, 103, 500 million numbers, using 16 go-routines or one go-routine on only one thread. We're a single-threaded Go program. Look at what's happening in these results. We can see here that it took 321 milliseconds for our single-threaded Go routine, our single Go routine, to add all those numbers up. Concurrent, we were using 16. It took longer. I ran it again just to keep things rolling. Single Go routine beat 16 Go routines, and we'll beat those 16 Go routines every single time. Why? Because we can't run those Go routines in parallel. So what does that mean? It means context switches are hurting us. Now, in Go, a context switch isn't costing you 12,000 instructions. It's costing you on average 200 nanoseconds or 2,400 instructions. But you're seeing how the context switches are slowing down the work. In this particular case, since it's CPU bound, if I can't run Go routines in parallel, I might as well just use one Go routine. But how do we see what happens when we can run 16 Go routines in parallel? Well, my machine is a 16-threaded machine. So if I get rid of that, we'll now see what the benchmark results are when the 16 Go routines aren't running concurrently on one thread, but are running in parallel on their own threads. And we should see the concurrent algorithms beating now the sequential one. So we see the same result for the sequential, we should. But look at the drastic improvement now once these 16 Go routines can run in parallel. Now those context switches are out of our lives. They're able to do that adding work much faster. Cool, right? I mean, this is what we expected. This is why when we're learning things, don't go into the mechanics. Don't go into the details, really, of how things are implemented. Implementation can change. I want you to understand behavior, because it's through the behavior that we can then write code and we can then realize either what's not happening or happening and help improve it. Now, what about our IO-bound workloads? Well, for an IO-bound workload, I did a couple of things here. We're going to generate a list of documents that we're going to simulate opening up, because I want to be able to do millions of them, and I can't just open up that many file handles. So what we're going to do is create the simulation of a 1 millisecond blocking read. And so read simulates a system call that will put the Go routine into a waiting state, and then we're going to do some extra marshalling work. And then we're going to have a find, where we do a single linear traversal, or find concurrent, where we do the same sort of algorithm. We break it up. And then for our test, we'll do the same thing again. This time what we'll do is we'll produce like 1,000 documents that we're going to open. We'll run them sequentially and we'll run them now. Now, what should we see when we run as a single threaded Go program? Let's go into IO-bound. What are we going to see? Remember what we said about IO-bound workloads. They do not need parallelism to see better performance. Now, again, I don't know if 16 is going to give us the best performance, but that's not important. What's important here is that, unlike our CPU-bound workloads, we should still see our concurrent workload running faster than the sequential, even when we only have one thread in the background, even when we don't have parallelism. Look at that. Look at the significant difference that concurrency gave us on our single-threaded Go program leveraging concurrency. We would never see that with CPU-bound, but we see it with IO-bound. This is why Go is so great for the types of workloads we're doing, because we can leverage each thread really to its fullest capacity, leveraging concurrency like this. And I don't need to worry about running things in parallel. Now, what happens if I use all 16 threads that can run in parallel on this machine? Sequential should never change. It's only using one of the 16 anyway. But I want you to notice that the concurrency numbers aren't necessarily any better. You might think, Bill, wait a second. What you're telling me is that using 16 Go routines for this workload on just one core and hardware thread is as fast as if I used all of your CPU capacity? Yep. Why? Because that 1 millisecond of latency is so large, it's so large that we're able to keep that one hardware thread efficiently busy. Parallelism here isn't buying us anything. In fact, I'd be wasting resources if I used 16 threads here, which really means that the hardware is available to anything else running on the machine. Mind-blowing, right? Super interesting. So this is really, stop sharing. This is really what I wanted to share with you today. I wanted to show you how just by understanding the scheduling semantics and bringing it into IO-bound and CPU-bound workloads and showing how context switch latency hurts us on the CPU-bound side. So we need parallelism to remove it. But on the IO-bound side, that context switch latency is helping us. It's working for us, not against us, and allows us to see this better performance even when we're a single-threaded Go program. And having these ideas and being able to identify when your workloads are CPU-bound or IO-bound will help you better architect your software, and then also kind of also be able to allocate the amount of hardware you really need. And so you're not over allocating or under allocating. All right, this is my presentation for tonight. So if anybody has any questions, now is a perfect time to ask them on the chat. I know we're recording as well, but if you feel comfortable speaking, that's good enough, or that's good as well.
Questions? Any questions? Any comments or jokes? Oh, there we go. Oh, Stuart just had a comment in the chat. He said, "Good job, Bill."
Thanks, Stuart.
Thanks for keeping up the energy at 10 o'clock at night.
Yeah, that's what it's all about. So let's do this. I'm gonna drop, actually, maybe I can share my screen. Let me share some information here. You all can see my screen again. If anybody ends up having questions later, tomorrow, whenever.
Well, so I had a question. I get the idea. So I totally get what you're talking about in the scheduler. I see all of that. How do you detect, besides just a lot of deep thinking, how do you detect when you're spending more time context switching than doing work? Are there built-in metrics? Is there something other than just, well, make sure you really pay attention to what your code is doing? Like, is there some other kind of obvious giveaways from the outside smells that say, you know, you're probably doing this wrong because you're wasting a lot of time context switching instead of giving your threads time to execute?
Right. So what's really nice, Carson, is Go has kind of eliminated some of that for us, because if we could get into the Go scheduler semantics, we can just kind of blindly throw Go routines at the problem. Mm-hmm. And Go is scheduling that at a high level of efficiency. Now, that being said, if you were writing these types of services, let's say in C, where you're working with operating system threads directly, and you know you need to use pooling, and you're really trying to figure out what's my most efficient pool size, and you just don't want to do it based on running load through the service and measuring how long that's taking. There is a tool in Linux called perf, but it's a Linux tool. I've never seen it. I don't believe the Mac has it or any other operating system. And this perf tool is going to give you all of that lower level OS information about context switches. It tells you about branch prediction misses and cache line misses, and it will tell you all of these things about your running program. And that would be one way that you can measure that level here in Perf. From the Go perspective, what I tend to do is focus on running workloads through the services and measuring how well we're doing with those workloads. And then I could take a snapshot of CPU or memory profiles or tracing and kind of inspect how the program is running until I find maybe that. And normally with Go, it's not going to be an adjustment on Go routines. It's probably 9 times out of 10 going to be an adjustment on how we're allocating and how much we're allocating and where we're allocating. Go has really kind of taken some of this off of our backs.
Sure.
And I'm so grateful for it.
Awesome. Thank you.
Cool. Well, with that, I'll go ahead. Just one more thanks to you again for speaking.